Hello again. In this video we're going to talk about the calibration process and how to achieve the good precision, and of course before of that how to get. Hello once again. In this video we're going to talk about the calibration process and how to achieve the good accuracy and good precision for our instrument. Now for every instrument we're using, we should be sure that the reading we're going to have is going to be an accurate reading. Other than that, all the reading we're doing are wrong. Now for example, if I get to set this value to 0 for the device, now I set the value to 0 by pressing the middle bottom here. Okay, now what am I supposed to have is that when I am going to open the device to any value, I'm going to have a reading. I need to be sure that this reading is correct. To do that, we need to make a measurement and compare this measurement to a standard value. It's something like when you are going to have the thermometer and you put it in the boiled water to get the 100 degree, and you put it on the ice to get the 0 degree. So that's what you call the scale, the thermal scale, or the heat scale. What we have here is we're using something called the blocks or the gauge blocks. These gauge blocks are standard blocks. You can see it have a shiny surface, and these blocks made of stainless steel. It always should be kept at the temperature of the lab, which is something about 20 degree to 25 degree, because any other change in the temperature may change its value slightly. Have a good surface finishing, and this is done by the super finishing process. And the main reason for doing the fresh, the good surface is to have very close tolerances when I get to do that. So you can see that if I get to slide these blocks against each other, then twist them. It's not magnet, but the two parts are going to be built up as one part. Now, by built up a certain thickness by using these gauge blocks, which have the thickness changed first by tens, we have them changed by half millimeters, we had them changed by the hundredth of the millimeters, and we had them changed by the thousandths of the millimeters. We can build up any value and use this value to check what is the accuracy of our measurement. Now what I choose here was 2.009 plus 2.01. So the adding of these two values should be 2.009 plus 2.01, and this will give me 2.019 as the reading I'm supposed to get from my micrometer. So I'm going to put the blocks in my micrometer between the parts and take the reading. Now the reading I have is 2.009 plus 2.01 is 4.019. What I got here is 4.018. So my device had an error which is less by 1 millimeter. I'll try to check another reading for that and see if I'm going to have the same error. If I'm going to have the same error, I will say that I have something called a systematic error for my tool. This systematic error means I need to record this error and always try to add or subtract the value of this error. Now the other part I'm having here is single block, and this should have the 2.39 millimeter for the thickness. And I'm going to put this one in and check the reading. So the reading I have here is 2.387. I should have 2.39. So now I have 0.003 error in the reading. In the previous one I had 0.001. So the range of the error I have for this device is going to be anything as in 3 in thousandth of the millimeter up to 1 in thousandth of millimeter. Of course, I should repeat this approach multiple times and do the value for the standard deviation, and then I will calculate what will be the percentage of the error of this device I should add or subtract from the measurement each time again to do the things. Now, actually, we can do that as a temporary solution, but to do the best option or to optimize your device, you need to send it to the lab and certified lab, and again to do the calibration for your device electronically, and they will give you a device that can read without any error. Now we're talking about the precision. If I get to measure the same part multiple times, and I get to pick one of the parts randomly again, and I will take the 2.46, and I get to set the value to 0. Okay, now it's 0 now. Okay, and I get to check the thickness of my part. Now I had 2.464. The reading is 2.464. Again, to move the part a little bit and do the reading again, I got 2.466. Now you can see that the things are getting higher. If I again to put the part in this location and take another reading, I got 2.466. Okay, I got 2.467. So the things are changing for the same, what's supposed to be a same thickness. Now that's what we call the precision. In the precision, that's the actual reading. My readings are going to be as close as possible to it when I get to do the reading. It's close to the mean value. That means my device had good accuracy and good precision. If this is the actual value, my reading is going to be always in this range. It's above or below. That means it has a good accuracy, good precision, because it's still doing the same range, but it have a bad accuracy. So the precision is good, but the accuracy is bad. Now what will be the reading of the situation? If this will be the mean value, my reading is going to be 1 here, 1 there, 1 here, 1 here, and 1 there. That means that my device had a bad accuracy and bad precision at the same time. So the precision is the repeatability of the readings within the mean value, within the mean value, close and within the mean value. This will be a good precision and good accuracy. If I get to have my readings within the same range, but it's going to be away from the actual value, this will be bad accuracy but good precision. If my reading is going to be distributed variably along the mean value, that means it have a bad accuracy and bad precision at the same time.